Hello everyone, this is the second lecture on HYSYS and Unisim simulations, and my name is Shekhar Bhattacharjee. Today we are going to discuss how to determine or estimate the thermodynamic and transfer properties using HYSYS and Unisim. Typically, let's say we want to use the values of, say, specific volume, we would be interested to find out values of internal energy. We might be interested in finding out the values of enthalpy. We might be interested in finding out the values of entropy, or let's say in terms of transport properties, let's say we want to find out the value of viscosity, dynamic viscosity, or we want to find out the values of kinematic viscosities, etc., etc. We want to find out maybe the values of specific heat. Now, finding out for pure compounds, it's kind of easy for pure compounds. We might use typical equations of states or different correlations. But when it comes to a mixture of compounds, so this is easy. But when it's a mixture of compounds, let's say a mixture of hydrocarbons, then it becomes extremely difficult. But using HYSYS or Unisim, estimation of these properties becomes very accurate as well as very easy, and we'll show you this with an example. Let us say we want to find out the specific volume. We want to find out the specific volume here. So here we want to find the specific volume V in terms of, let's say, meter cube per kilomole of normal butane, so C4 and C4 at 500 Kelvin and 18 atmosphere pressure, using Peng-Robinson equation of state, which is a very good equation of state for hydrocarbons. As well as we will show you how to estimate the same specific volume, or for that matter any property, using another equation of state which is also very popular, which is Swaff-Redlich-Kwong equation, which is SRK equation of state. I have given you the values, but we will show you how to calculate these values. But this is for a pure compound, and once you know how to do it for a pure compound, estimation of these properties for any mixture of compounds becomes very easy. So let us start using the simulation software. We open a new case here, and we go for view. Here we add normal butane. So this is normal butane here, and we add the pure compound. So this normal butane is added. So we have to now use an equation of state. So we go here, fluid packages, and we do add, and we go down the list, and we find out here Peng-Robinson equation of state. So that is already selected here. So we just cross it out, nothing else. We just cross it out. And then we go to the enter simulation environment. So we go here. Now let us just take a stream here. So we take a stream here, and we name this stream. So by default it comes as 1. Let's call this as normal butane. Okay. But here you see the temperatures are given in Celsius. Temperatures are given in Celsius, as well the pressure is given in kilopascals. But in our case, here the temperature, in our case, if you see here, the temperatures are given in terms of Kelvin and 18 atmosphere pressure. Of course, it really does not matter, because when you enter in any unit, automatically the simulation software converts that to its convenient or the displayed unit. So in this case, it will be, even if we enter the values of 500 K, this will be converted to corresponding Celsius. So I'll just show you. If we enter 500 Kelvin here, automatically this shows the corresponding Celsius. But let's say we want to see it in terms of Kelvin. In that case, you have to change the parameters here. For doing that, what you do, you go to the preferences here, and under the preferences, you go to the variables here. And for these variables, here for this user, so you just say clone, and you go down all the way, to, let's say, temperature here, temperature, and here you just say Kelvin. And similarly, let's say you want to change the pressure unit, so go down to the pressure unit, and the pressure unit is given in kilopascals, but you want to change it to, let's say, atmosphere. So here we click on atmosphere. Now you just click close it, and automatically you see this comes in Kelvin and this comes in pressure atmosphere. Okay, so now we start entering the values given in our problem sheet, which is right here, 500 K and 18 atmosphere. So we go here, we enter the value as 500 Kelvin. You see 500 Kelvin, it has already been given here, and the pressure is, let's say, 18 atmosphere. And of course, we have to define the conditions, composition here, and the composition is pure butane. So I put here 1 and hit enter. This window comes in. Since this is a pure compound, so mole fraction is 1. So I just give OK here. So I go back to the condition. So 3 parameters already defined. So you see the composition is already defined, the temperature is already defined, and the pressure is defined. Now you have to give the flow rate, because for this simulation softwares you have to give the 4 parameters. So although for estimation of the thermodynamic property, flow rate really does not matter, but you have to give value. Any value will do. So let's put here the molar value. Molar flow rate is equal to 1. And automatically you see this turns green, showing that the values are given. But we don't see. So here, so this problem is defined and it becomes deep blue. So you see here, you see all the values here, but you don't see the molar volume. To see the molar volume, what you do, here you go to this workbook here and you say setup. And under the setup, you see all these parameters which are displayed here are shown here. So let's say you don't have the liquid volume flow rate right now, so you say delete that one, but you want to add the molar volume. So here under the add, so what I did here, I clicked on add, so this list comes in. I go all the way down to molar volume here, and I just say add, and automatically you see this molar volume comes in here, and the value is shown as 2.025. So if you do the manual calculation using hand calculation, you'll get exactly the same value. So you see, using the Peng-Robinson equation of state, the specific volume of normal butane at 500 Kelvin and 18 atmosphere is 2.025 meter cube per kilomole. Now, let us say we want to see what will be the value if I would have used SRK equation of state. That's very easy. You come here, and what you do here, you go to this beaker, this one, and now here you see on the fluid package here, you say add. And under the add, you go down and you use SRK. Here is the SRK equation of state. You click on that one. So that is now chosen. So this is now basis 2. So in this case, we have been using basis 1, which is Peng-Robinson equation of state. Instead of that, let's say we are using basis 2. That means I would be using SRK equation of state. So once that is done, you come back and you see the values here. You go to the simulation environment. It says, do you wish to be left in holding mode? You say no. So you come here and you see this is 2.058. So this is the answer. So automatically it has now calculated the molar volume using SRK equation of state and not Peng-Robinson equation of state. So you see the value what we had here is 2.058. So you see we have calculated the value of specific volume of normal butane at 500 Kelvin and 18 atmosphere using both Peng-Robinson equation of state and SRK equation of state, and the difference in the values is not much, almost negligible. This is 2.025 meter cube per kilomole and 2.058 meter cube per kilomole. Now I'm going to show you one more very interesting technique. Now here you have calculated the value of the specific volume. For that matter, any property what I have said could be the internal energy, enthalpy, entropy, could be any other that specific heat, molar specific heat, or could be viscosity, any property at one particular value, which is 500 Kelvin and 18 atmosphere. Now let us say you want to see at the same pressure 18 atmosphere, if I vary the temperature, how that particular value of the variable changes. Let's say in this case, how the value of the molar volume changes at 18 atmosphere pressure for normal butane if I vary the temperature between 450 K and 550 K. These data are very important for designing. Now you see, using the simulation software, this becomes very easy. What you do here, you just go to the tools menu here and you go to the data book or control D, and here you go for insert. For here N-butane, that is a stream you have. Under the N-butane you go all the way down to molar volume. Here's my molar volume, and you say add. You see, automatically this molar volume comes in here in this particular window. Next, of course, we want to change the temperature, so that must be selected also. So here you come here and you click on temperature and you say add. So you see temperature has been also selected for the same stream, normal butane, non-butane. It could be, this could be for different other stream in a very complex simulation problem. It could be like one particular variable in one stream and how that changes if you vary that, how that changes at any other particular variable in another stream. That could be very easily seen also. So it's a very powerful tool. Okay, so once you have done that, you have selected the variable, so you cross it out. Now you kind of like expand this one. You go to the case studies and you give a name here. Let's say case study 1, and you kind of like hit enter. No, you just say case study 1, and you say add. Automatically this comes here, case study 1. Now you see there's an option, it's independent and dependent variable. Now here you click on temperature as independent variable because you want to change the temperature. And by changing the temperature, you want to see how the molar volume changes. Therefore, temperature is now independent variable and molar volume is your dependent variable because the value of the molar volume depends on how you change the temperature. Once that is done, now you click on view. In the view, first you give the low bound, which is 450K. You see here, 450K to 550K. We want to see how the molar volume changes. So we go here. So we put here the value as 450 Kelvin. And this one high bound is 550 Kelvin, and step size, let's say we want to see how the value changes in a step size of 20. So this is done. Once that is done, so you have selected your variables, you have given the high low range and the high range and the step size for your independent variable, which is the temperature. Now you say start. Once that is start, you don't see much, but once you go to the results, you see it shows in the form of a graph how the molar volume changes, what are the values of the molar volume if you change the temperature between of normal butane, if you change the temperature between 450K to 550 Kelvin in terms Kelvin. And also, if you want to check the values, instead of this graph, you click on this table radio button and this gives you all the values. Now these values could be exported to an Excel sheet, and in my later videos I'll show you how to export these values very easily. But as you have seen, this is just so easy to calculate how by changing one particular variable in any stream on any particular portion of your simulation or on your flow diagram, how changing that variable changes the value of another variable. Let's say if you change the temperature of your feed, how the yield changes in the reactor on the later part, somewhere down the line of your simulation program. So that could be done in a just matter of seconds. So it's that easy, and it is an extremely powerful software. So that pretty much concludes the demonstration for this particular video, and thank you very much. I'll see you again in my next lecture.